My name is Mark Kurtz, and I'm the Director of Machine Learning at Neural Magic. In this video, I want to introduce you to the world of sparsification and how Neural Magic combines state-of-the-art algorithms and optimization techniques with our deep sparse inference engine, enabling GPU-class performance for your deep learning models on commodity CPUs. So what exactly do we mean by sparsification? It's a collection of well-researched and documented techniques for removing the redundancies from deep learning networks, resulting in smaller, faster, and equivalently accurate models that can be deployed anywhere. The trend in deep learning has been a consistent increase in the size of the networks, with the largest topping out at hundreds of billions of parameters. And it's no surprise that not every parameter in those larger networks is needed. What may be surprising is that this logic applies to even the smallest neural networks. It turns out that at deployment, most of the weights are actually useless. Pathways that were important for a large optimization space while training become unneeded as the training process converges on a solution. These unneeded connections can safely be removed from the network, a process called pruning. Pruning results in sparse networks with fewer parameters, and therefore less compute is needed to run the model. Just how many connections can be pruned from a network? A lot. Generally, we can easily remove 80% of the weights without affecting accuracy. For highly optimized models, that can stretch to 95%, where only 5% of those large networks is actually needed. Pruning is further broken down into two main categories: unstructured and structured. Unstructured removes individual weights and connections from the network, while structured removes large sections such as channels, filters, or layers. So structured changes the shape of the network and underlying tensors, while unstructured does not and instead introduces zeros into it. Due to the additional flexibility of unstructured, it generally results in much higher sparsities as compared to structured. Now, not only are most weights useless in deployment, but they're also too precise. The precision necessary to enable the small weight updates during training is no longer needed at deployment time. This extra precision can safely be removed in a process called quantization. Quantization results in compressed networks that lessen the compute and memory needed to run the model performantly. Weights and activations can generally be safely compressed from their standard FP32 representation to int8 without affecting accuracy, a 4x reduction. Advanced quantization techniques can push the compression even further down to int4 and even 2 bits in some cases. Quantization is further broken down into two main types: dynamic and static. With dynamic, the activation ranges are calculated at runtime to compress the FP32 distribution into an int8 one. For static, a sample distribution is collected offline, and at runtime, the activation ranges are compressed using the values from that sample. These differences lead to different impacts on accuracy and performance. Dynamic is generally better for accuracy recovery, but it's not as performant as static. To help with accuracy recovery for both pruning and quantization, distillation can be used. Distillation uses a teacher network during training to better guide the desired model to the correct solution. This works by leveraging the teacher network to create a smoother loss surface by adding additional information for the student to learn from. For example, a classification model that incorrectly classifies a bus can learn from the teacher that it is a bus and is also related to trucks and cars in visual appearance. Distillation is traditionally used to distill a large model's knowledge and accuracy into a smaller one, but it's increasingly used alongside pruning and quantization. Finally, combining some or all of these techniques is what we refer to as compound sparsity. A common pathway combines pruning, quantization, and distillation to create sparse quantized models that far outperform the baseline model and any technique applied individually. You may ask what the range for the sparse quantized models outperforming their baselines is. Maybe 25%, 50%, or even 200% faster. No, combined with our deep sparse inference engine, these sparse quantized models can run over 40 times faster, as shown in our latest MLPerf results for the throughput on BERT large. 40x can be at the extreme end, but we show at least a 4x increase in latency performance and at least an 8x increase in throughput performance for common ML use cases. This means you can respond to your users faster, run on cheaper instances, or replace your current model with a larger and more accurate one while maintaining the same performance. Now, I mentioned at the beginning that sparsification is well researched, but the challenge is that these methods are not applied equally to all target hardware platforms. For example, unstructured pruning does not take well to GPUs, and quantization isn't supported for speedup on certain types of GPUs and CPUs. Not only this, but determining the proper algorithms, implementing them, and then tuning hyperparameters to sparsify your model adds additional complexity and time. This complexity leads to a lack of adoption and confusion on what to do despite the dramatic performance increases. Our own polling shows that well over half of machine learning practitioners aren't sparsifying their models at all. At Neural Magic, we're not only focused on state-of-the-art performance and algorithms, but also on making it as easy as possible for you to achieve the performance on your own data. We've built a complete set of tools to provide recipe-based approaches to sparsifying your machine learning models. These tools include SparseML, which applies sparsification techniques in only a few lines of code for most ML pipelines, and the Sparsu, which hosts pre-sparsified models and the associated recipes. The combination of these tools enable you to achieve performance on your models in a few different ways depending on your requirements. First, you can apply model sparsification in a training-aware approach where the algorithms are applied during training to achieve the best performance and accuracy. Second, you can apply the algorithms without retraining by using one-shot techniques to achieve some speedup quickly. And finally, you can sparse transfer from our models, so you don't have to worry about any of the sparsification hyperparameters and achieve great performance and accuracy easily. Be sure to watch our sparsification from scratch demo video in the series to see this in action. Thanks so much for joining me in this overview of sparsification. Be sure to check out my colleague Michael Goen's deep dive into the DeepSparse engine itself to learn how we now take these sparsified models and run them in the most efficient way possible all the way down to the silicon. Thanks again for watching.